Okay, welcome to example 1D on page 106. The instructions to this example are actually on the previous page, so let me read those to you. They're giving us a matrix and asking us if the matrix is diagonalizable. That's the first question. And if it is, they'd like us to decompose the matrix using that formula, D equals Q inverse AQ that we talked about earlier. Okay, so we're going to do this problem and try to use the theorems back on page 104 that we just discussed. Okay, so this comes down to eigenvalues and eigenvectors, so that's going to be our first step. Okay, so we'll take the determinant of A minus lambda I. Okay, and let's see, we've got a bunch of zeros kind of sitting over here in the third column, so that's kind of a natural choice to expand down. And if you do that, you're going to get negative 1 minus lambda, okay, times the determinant of the 2 by 2 that looks like this, 8 minus lambda, negative 9, 6, negative 7 minus lambda. Okay, we'll do some algebra here. Okay, so let's see, if we take the determinant of that 2 by 2, it's going to look like 8 minus lambda, negative 7 minus lambda. Okay, and we'll do a little bit more algebra here, so maybe take out a minus sign from that first term. That's going to be a lambda plus 1. And then if you do the algebra inside the brackets here, okay, and simplify a little bit, here's what you're going to end up with. Lambda squared minus lambda minus 2. Okay, and that quadratic also factors. Okay, and in fact, one of the factors of that quadratic is lambda plus 1, so that's going to give us 2 of the lambda plus 1s and an additional lambda minus 2. I'm skipping a few of the algebra steps there. Okay, so how many eigenvalues do we have here? Okay, well, if you were to set this equal to 0, you can probably see that there are going to be two solutions to this equation, either negative 1 or 2. And using the language that we kind of developed on page 104, we could say that the multiplicity of the eigenvalue minus 1 is 2, and the multiplicity of the eigenvalue 2 is 1. Okay, so now we're ready to find eigenvectors, starting with lambda 1 equals negative 1. Okay, and I'm going to just go through these calculations a little bit quicker because we've done this so many times. So if you go back to your matrix A minus lambda I, substitute in lambda equals negative 1, here's what you're going to get. You can double check my calculations. Okay, and that matrix reduces down nicely to this. Bunch of zeros in it. Okay, so I see one pivot position right there, so we've actually got two free variables. So we'll make x2t and x3u, and if you take that first equation and solve for x1, you wind up just getting t in this case. Okay, so can we write down a basis for the eigenspace associated with this eigenvalue? Okay, well, we'd start by maybe letting t be 1 and u be 0. That's going to give us 1, 1, 0. And then we'd move on and let t be 0 and u be 1. That's going to give us 0, 0, 1. Okay, there is a basis for E lambda 1. Okay, and we've taken care of our first eigenspace. All right, and we're ready to look at the next eigenvalue. So lambda 2 equals 2. Substitute that into our matrix, A minus lambda I, and here's what we're going to get. Okay, and if we row reduce that, we will come down to a matrix that looks like 2, negative 3, 0, 0, 2, negative 1, 0, 0, 0. Okay, notice this time, two pivot positions, so we've only got one free variable, and it's x3. All right, there's a little algebra to do here. This matrix is not so nice, so I'm going to go ahead and just show you what you wind up with for x2 and x1, and you can do these calculations on your own and confirm that what I'm doing here is really correct. Okay, we get 3/4 t for x1 and 1/2 t for x2. Okay, and that leads us to a basis for e lambda 2 that just has one vector in it. Okay, what would be a convenient value for t to choose here? Okay, well, because of that over 4 that you see up here, t equals 4 might be a nice number to choose. I'm going to choose that, and if you do that, you're going to get, let's see, 4 in for t is going to give us a 3 in the first position, a 2 in the second, and then a 4 in the last one. Okay, so there's a nice basis for e lambda 2. All right, so question for you. Based on our calculations, is the matrix that we started with diagonalizable? Okay, well, that comes down to the question of, do we have enough eigenvectors? Okay, and if we go back to the characteristic polynomial, -1 had a multiplicity of 2, and we got 2 eigenvectors, so far so good. And 2, the eigenvalue 2, had a multiplicity of 1, and we got 1 eigenvector. Okay, and since the number of eigenvectors agreed with the multiplicity in both cases, we know, okay, by, I believe it was theorem 5.9, that we do indeed have a diagonalizable linear operator here. Okay, so the answer is yes. Okay, and actually it's not a linear operator, it's just a matrix in this case. So the matrix A is diagonalizable. And they also asked us to write down the matrices Q and D that kind of go with this. Okay, remember, those Q and Ds had very special forms, so Q, we can form that matrix by just making its columns our eigenvectors. So let's just choose an order. Okay, so we'll start with 1, 1, 0. That's the vector up here, and then 0, 0, 1. We'll make that our second eigenvector, and then finally 3, 2, 4. Okay, and D was a diagonal matrix that had our eigenvalues along the main diagonal. And all we need to be careful of here is to go in the right order. Okay, so first eigenvalue needs to go with the first eigenvector, the 1, 1, 0. What was the eigenvalue for that one? Well, that went with e lambda 1, so eigenvalue that goes with that eigenvector is -1. And then we move on to the second eigenvector 0, 0, 1. That also went with lambda 1 equals -1, so we've got another -1 to match that second eigenvector. And then finally 3, 2, 4, that eigenvector went with the eigenvalue lambda 2 equals 2, and so we're going to get an eigenvalue of 2. Okay, and so our diagonal matrix just looks like